All right, demo number 1. We've got 2 stoppers here. I added a stopper to my string, and now we're swinging it around. And all right, same direction as what I put on my diagram. So swing around like this, and we've got the inside stopper and we've got the outside stopper. And tell me about how they are moving relative to each other in their spins. Same velocity, sort of. All right, so when they're right here, they're both along this line, and then they spin up to here, and who went farther? The outside one went farther, but who's spinning faster? The middle one's spinning faster. Okay, what about when they get over to here? Tell me about the angle that they've gone through. So when they go from here all the way over to here, tell me about the angle they've gone through. It's the same angle? All right, so if we're looking at the kinetic energy on these guys, you would probably naturally just go 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And you get the kinetic, then we just keep, if I had more stoppers on here, we just keep adding more, m3 v3 squared and so forth. And they have the same angular speed. So when this guy goes all the way around the circle and gets back to there, he's gone through 1 full circle. And when the outside guy goes through 1 full circle, he's gone through it. Same angular speed. They go through the same angle in the same amount of time, but they have different linear speeds because the radius is different. We've got R1 and R2. We've got 2 different radii. Linear speeds because radii are different. So if we're going to rewrite this in terms of the angular speed, and remember that the angular speed is, so let's see here, V is equal to R omega. So if we've got V1, we've got R1, and we've got V2, we've got R2, but the omegas are the same. So if we rewrite this guy, we're going to have 1/2 m1 R1 omega, but then this puppy gets squared, and then 1/2 and m2, and that guy, and they get squared. And now let's play with the equation because we have a mess of an equation, and let's see if we can figure out some way to clean it up. And I'll need that later for my freshman. I actually got to start physics with my freshman. It's so great. Finally not to be talking about biology. Play with toys. All right, playing with this equation. So let's see here. What's the same between both terms? We've got a 1/2. That's the same. The masses could be, I picked out 2 stoppers that are identical, but they could be different. So those guys could be different. The positions are definitely different, but then the omega should be the same. So okay, E, we're going to have 1/2, and then this guy, and this guy, and then the omegas are the same. So we're going to factor the 1/2 to the left and the omegas to the right. And we're going to give this guy a special name called rotational inertia. Rotational. And we'll call it capital I for inertia. Very poetic. Wait, what? Yeah, we also use I for impulse. Sometimes impulse is J. But J also has other meanings. So everything's going to get double and triple used eventually. All right, so what do you notice about the rotational inertia thing here? Well, let's see here. How important is position versus mass? Are they equally important, or is somebody more important? Yeah, they are. That's way more important. How do you tell that? Well, that's the thing that's squared. So position more important than mass. I'm not saying mass isn't important. I'm just saying you look at the equation, you can say, wow, I know what's really important here. It's the thing that's squared, so it blows up really fast. Other thing that we notice is that we've got a little tiny blob that's small relative to the radius of its circle. And then we've got another tiny little blob. And then what we're doing with them is that we are adding up the individual pieces to get the overall rotational inertia. Because by adding the second guy on the inside, this is now going to be harder to swing. It's got more inertia to get going than it did before because I added more mass to it at a different place. So the simple parts add together to make composite object. And I could add a third stopper and a fourth stopper and a fifth stopper. And our general thing here, would become, I'm going to add up all little masses and all little at each position. Oh, I should add a third dot here. I hope you left space. Each mass has its own corresponding. This should sound like something else that we've talked about in this class. Each mass has its own position, and then we're going to add them all up. What was that? That was the center of mass thing? Yeah? Except that the difference with that is the position wasn't squared. Now the position is squared. And we're going to go from 1 to, well, how many pieces do we have here? All right, this is going to be some guy that you really need to know and be familiar with and get. So we're going to have to pause here for a day. And I have a few, let's talk about that for a second. Position is more important than mass. So here we go. I have this guy. So if I put a mass on the end of a stick and I balance, have I done that in here before? Did I do that when I was talking about the center of mass and balancing thing? And it's going to, okay, now, did I then flip it over? Right, and this guy falls down a lot. It's a lot harder to balance. It falls down a lot easier. If you change this guy, you're going to change the inertia of the thing. All right, more inertia is going to be more stable. It's going to be harder to rotate. So when this is really far away from the pivot, which should be my finger, it'll be a lot easier to balance. And if I practiced, I could probably keep my hand almost still. Whereas when I turn it upside down, it's a lot easier for it to fall over, and I'm going to chase it all over the place, and then it's going to fall relatively quickly, even if I'm concentrating on it. So now don't smack each other with these. But, so I'm going to pass these around, hold them at 50, spin it, see what that feels like, pass it on to the next guy, then hold this guy at 50, spin, ooh. You know what, that lasted for a good 15 years. Where was I? All right, you guys all, you know what that feels like now? Went around, everybody got a chance to play with it. So this is, you're spinning it at the 50, and this is at the 40, and this is at the 60, and that guy is 200 grams, and this guy is 200 grams, and then this guy is at the 10, and this guy is at the 90, and this is also 200 grams, and this is 200 grams. All right, that's just the numbers for what you just felt. The rotational inertia is going to be, let's add up the pieces. And I picked 200 grams because 200 grams is enough more than the stick that we're going to pretend the stick doesn't have any mass, even though it does. So the mass is 200 grams. Now, what matters is not the 40 or the 50 or the 60. What matters is how far is it from where you were holding it and spinning it. So this should be 10 centimeters. So this R is going to be 10 squared, and this is going to be, again, and 10 and squared. And we're going to get, well, 200 plus 200 is 400 times another 100, and this is going to be gram centimeter squared. Now, how bad was that? Meh. Okay, let's do it again for this guy. Same starting point, m1 r1 squared plus m2 r2 squared. And now it's, well, this is 50, now it's 40. So same 200, 40, 40. So let's see here, 40 squared is going to be 1600. And 1600 times 2 is 3200. And then we're going to add some more zeros. And then we're going to add them together, so we got 64. And then 0, 0, 0, 0. And same units, because we're still, that's still grams and that's still centimeters. Gram, centimeter squared. All right, so we moved. So let's see here. R goes to 4r, then I goes to, okay, if the distance, because we went from 10 to 40, the radius increased by a factor of 4, yes? So what did the rotational inertia increase by a factor of? If we take this guy and divide by that guy, what do you get? 16? 64 divided by 4 is 16? Oh, also known as 4 squared. So 16i. So you could either brute force it and calculate it all over again, or you could use the relationship and say, well, if I increase the radius by a factor of 4, I need to square that, and that's going to tell me how much the inertia is going to increase by. Now, we don't have to swing it like a baton. Oh, question. So so A. Let's call this A. Let's call this B. So IA is this, and then B, and then IB. So let's see here. IB is 16A. Right? The original rotational inertia, you multiply that by 16, you're going to get the new rotational inertia. Does that help? Okay. Now, we don't have to swing it like a baton, hold it in the middle, and spin it around. We could swing it like a baseball bat and hold it at the end and swing it. All right? Now what is the radius if I'm holding at the end and swinging at the end? Do they have the same radius? No, because this guy's now going to be 40 and this guy's now going to be 60. I've just shifted everything to the side. All right? So this is 40. This is 60. All right, we're going to pass this around again, and I want you to spin it in the middle and feel this. Then I want you to hold it down near the end. I mean, don't do it like so you're just actually have your hand on the stick and spin it and see what that feels like. You're going to notice that it feels different, and you're not moving the masses on the stick this time. What you're doing is you're just moving where you're holding it and spinning it around a different place, and you're going to notice that it feels different, right? Yep. Anybody play baseball or cricket ever? Yeah? Okay. Suppose you're at bat and you swing and your swing is late. Okay? How do you deal with your swing on the pitch is late? What does the coach say to do? Choke up. So that means you move your hands towards the top of the bat. Now the bat is effectively shorter, and Ian, you're about to smack him in the face. Fine, since we're doing A, B, let's do C. All right, so now we're going to do 40 squared and 60 squared, and I don't feel like doing that in my head. I'm getting, wow, that's a big number. And I'm getting over 1 million grams centimeter squared. All right, now, what if we melt down the metal and we spread out the metal over the stick? All right, now we don't have a chunk of metal. What we have is a smooth extended piece of metal, and that means the adding the chunks is going to turn into this smooth summation. And we're going to go from algebra to calculus. And what we're also going to do, instead of having different chunky masses, we're going to melt the mass down and make them all be the same tiny little mass DMs. And we've done this before. And the reason why we did the center mass thing before is so that we could do this now and not have you guys have panic attacks. At least that's the goal. May or may not work out that way. You might still have a panic attack because now you know the pain that is coming and it makes you flinch. All right, so let's get a uniform stick. Here we go. We got a uniform stick of mass M, and length L, and we're going to spin it around the middle. All right, but now we're going to have to do the calculus thing. And because we're spinning it, this is 0. This is 0. Okay, now if I head to the right, usually we make right positive. So if I head to the right, this guy's going to be L over 2. And what's going to be the distance to the left? Negative L over 2. That negative is actually going to matter. The negative is going to matter. And we've talked about linear density. As soon as you have an extended object, you have to deal with the density of the object. And your favorite word is going to be that, because that cuts down on the calculus. All right? And it makes it so that you can set up a ratio. We've got a homogeneous mixture here. If we're going to go back to general science, which for you guys, that might have been like 7th grade, when you were talking about homogeneous mixtures versus heterogeneous mixtures. Solutions, that stuff. So this is a uniform object. It's all the same. It doesn't matter where I slice it or how big I slice it or how small I slice it. It's going to be the same density all the way down. And we're going to be able to get rid of dm from our integral that I'm going to write right there. We're going to be able to get rid of the dm and put it in terms of dx. We've done this before. This should look familiar. And our summation that we had, it was on the last board, but we're adding up the individual pieces. Now it's going to be this guy. And we only have one integral to do here because this guy gets to be a ratio. And again, I don't know how to add up the masses, but I do know how to add up the distances, so I can make this substitution. You always have to get rid of the dm and put it in terms of dx. Always required. So we're going to go r squared integral m over L dx. Wait a second, I've got an r and an x. Well, I've got a stick here. So this r, in this case, is going to become an x because I'm going to be walking down the stick. And it only becomes an r when I'm spinning the whole stick around. As soon as I spin the stick around, then I actually have a radius. But what I'm going to be doing is I'm going to be saying, hey, this guy right here is a little tiny mass that's spread out a little tiny distance dx, which the whole chunk is a distance x away from the axis. And that distance x from the axis, we're going to start way down here at negative L over 2, and we're going to walk all the way across until we get to L over 2. So our limits of the integration are going to be minus L over 2 to L over 2. And those of you in calculus should be okay with this. Those of you not in calculus, I don't expect to be all that okay with this. Certainly not at the beginning. This is one of the, congratulations, you've reached the stage of your academic career where you will not really understand something the first 30 seconds the teacher starts talking about it. It's going to take some effort. And then you still might not be able to. All right, so let's rearrange this thing. Constants, they get to go along for the ride. All right, once I clean it up and it looks like that, do we know how to deal with that? Yeah, well, I sure hope so, because we've done that a few times. So, antiderivative of x squared dx. X to the third over 3. So increase the exponent by 1, divide by the new exponent, and the m over the L get to go along for the ride. So we're going to do m over L, and we're going to have x cubed over 3. And then we're going to evaluate it between the limits. And notice how now that we have an odd exponent, that negative is going to show up again. That's really good. It would be unfortunate if it didn't. And then we plug in our limits. So, hey, can we move the 1/3 out front? Because it's just a number. So we're going to have m over 3L. And then we're going to have this whole thing cubed. So L cubed over 8 minus this whole thing cubed. Negative L cubed over 8. And I hope you can see why that minus sign is so important, because if without that, then we end up with a 0. And clearly not 0, because you know what swinging a stick feels like. Not the same thing as swinging a lightsaber, which doesn't have any mass. We add those two guys together. Okay, so L cubed over 8 plus L cubed over 8 is 2L cubed over 8, also known as L cubed over 4. All right, and then we got L cubed up there and then an L down there, so that kills one of those guys. So let's see, and then we've got a 4. So this is L cubed over 4. Okay, third and a fourth is a 12th, so we got 1/12 mL squared. Now, does it follow the correct form where we have a mass times a distance squared? Yes, it does. Good. And then we have some fraction out front, right? All rotational inertias are going to follow this. They're going to have some fraction out front, and then a mass, and then either a length, in the case of a stick, or a radius, in the case of something round. radius, squared, and the radius has to be squared. All right, so how bad was that actually? Not your favorite thing, but you don't need to go like take a nap or something or sit in the corner, suck your thumb. Good, let's do it again. All right, so we got the stick around the middle, we got the stick around the end, we got the different shapes that you need to know because we're going to put them together in different ways. And yeah, all right, so for right now we're going to have this hoop or the disc, and we're just going to have it spin in place. And then in the next chapter, we're going to say, yeah, but the thing to do with stuff is to make it roll. And what is it spinning around now? It's not spinning around the middle. What? Yeah, it's spinning around the bottom. That's the pivot now. We're moving the pivot from the middle to the bottom in order to have the thing roll. So that's where we're going with that, which is going to be painful.